Hello again. Well, our previous work has taken us to the point where we're pretty adept at solving variable separable differential equations, and we can solve readily first order linear differential equations. There are other equations that don't look like either of those, but with a simple substitution can be transformed into something that we do know how to solve. So these are really just algebraic transformations that will take an equation to something that we can readily solve. And the kind of give away the big result here before we start, but the substitution I want to talk to you about today would be if we have an equation y prime is equal to f of ax plus by plus c. Kind of looks like a polynomial on x and y, doesn't it? If we have an equation that can be put into that form, then if we let v equal ax plus by plus c, we can transform this equation into a variable separable equation. Now, I guess I will do that time permitting. I will do this theoretical computation toward the end, but for right now, let's go ahead and try a simpler equation and see how this thing works out in reality. So suppose that we had a y prime is equal to x plus y plus 3 squared. Now you recognize that as an example of this. There's some function of a coefficient times x plus a coefficient times y plus a constant, some function of that. In this case the function is square and the coefficients are 1, 1, and 3. Then what we want to do is to let v equal ax plus by. I don't want to do that for the generic, though. I want to do it for the particular because we're going to work on this problem right here. So I'd let v equal x plus y plus 3. Now, let's solve this for y. And I would get y is equal to v minus x minus 3, so that y prime would be equal to, and now here we'd use the chain rule, but you know it works out pretty simple. This is going to be dv dx times dx dx using the chain rule, and dx dx is of course 1. So right here I'm going to get v prime. Is that a good enough v? I should maybe open this up just a little bit. I'm going to get v prime, and then x differentiated with respect to x would be 1, and the 3 differentiated with respect to x would be 0. And from this I get v prime is equal to y prime plus 1. Okay. And we've also got that y prime is equal to, you see, y prime, this is my original differential equation, is x plus y plus 3 squared, but I'm using the substitution x plus y plus 3 equals v, so y prime is v squared. And these are both true. I'll put a bracket around it like simultaneous equations. Well, where do we go from here? Well, from here, if y prime is v squared, then I can write, and I'll give us a big therefore, v prime is equal to v squared plus 1. v prime is equal to, well, y prime is v squared, so v squared plus 1. v prime is equal to v squared plus 1. You recognize what we've got here? This is a variables separable differential equation, first order ordinary differential equation. So we would write 1 upon 1 plus v squared dv is equal to dx we were using for the independent variable. And then we've separated the variables, and so you know the next step would be to integrate these. And the integral of 1 over 1 plus v squared, if you forget, because it's been a semester or two or maybe 3 since you've had calculus 2 where you would have worked on that integral, if you forget, the inside front cover of your book has got tables of integrals. So you could look that up and see that that's going to be a tan inverse. Or I think that's the most convenient, but almost as convenient, you can use your cell phone or you can use your computer and you can go to Wolfram Alpha and you could ask for a little help. Or maybe you remember, maybe you don't need to look that up. If you look at Form 17 in the inside front cover of your book, though, you'll see that what we have next, integrating the left-hand side, is arctan, which I usually write as tan inverse, v is equal to x plus an arbitrary constant. And now we don't want tan inverse v. The first thing we want is v, and then of course ultimately we want y. So if I take the tangent of both sides here, I get the tangent, well, I'm not going to write down taking the tangent of both sides, I'm just going to do it. So when I take the tangent of this side, tangent of tan inverse, I get my v, and this would be tangent x plus c, and that looks real nice. But v is, come clear up here, v is x plus y plus 3, so that's what's equal to tan x plus c, or y is equal to tan x plus c, that got up a little high, didn't it? Sorry about that. And then transpose these, so minus x minus 3. And this has an arbitrary constant in it because this is a general solution. If it was an initial value problem, then at this point we would solve for c and find a particular solution, but it's not. It's not an initial value problem, and so we've got a general solution and we're done. And you see how that went. But I'm going to do at least one more for you, and let me scroll the screen up, and you see that the technique really doesn't vary. So an example from page 72 of our textbook, problem number 17, says that, let's change color here so there's no confusion about the color. I guess we'll just go to a red. This should be a lovely shade of red. We've got y prime is equal to 4x plus y, and that's squared. So again, y prime looks like a polynomial in x and y, ax plus by plus c, so it's first order in x and y. and the c is 0 in this case. So we would try to follow the same procedure that we did before. We would want to let v, I guess we'll go this way, we'll let v equal 4x plus y, so that v prime would be equal to 4 plus y prime, and now and y prime would be v squared. This is what we let v be. So y prime would be v squared. So v prime is equal to v squared plus 4. And finally, this is variable separable. So if I rewrite this separating the variables, I get 1 over 4 plus v squared dv is equal to dx. And I've separated the variables, which is the proof that this was a variable separable equation. So we would integrate both sides, and I don't want to make a mistake here, so I did this before we sat down, and I'm verifying things as we go by here. So this is going to be tan inverse v over 2 equals x plus c. It's worthwhile reviewing. It's not necessary, but it's worthwhile reviewing how this is integrated. But it's a trig substitution, and just kind of fun to play with. If you wind up with time on your hands, you could do some calculus too instead of watching a movie, I guess. All right, so if we continue this solution, you probably multiply through by 2, and then you take the tangent of both sides to get rid of the tan inverse, and that's going to lead you to ... That's going to lead you to v is equal to 2 tangent 2x plus c. But we didn't really want v. That was just a step along the way. What we really wanted was y. But I see that v could be replaced by 4x plus y. So this would be 4x plus y is equal to 2 tangent 2x plus c. And finally get y to stand alone to get an explicit solution. So y is equal to 2 tan 2x plus c, like that. And that also was not an initial value problem, and so we'll be happy to have here the general solution. Now we're going to learn 3 or 4 substitutions that are very, very useful in this general level of differential equations. And again, you don't have to memorize all this. I would create note cards for myself if I were you. That gives me a really convenient little dictionary to look up the different forms that we might put differential equations into. Remember that we have emphasized that solving differential equations, there's scant general methods, but if we classify the differential equations, there are a lot of classifications on which we know how to find general and particular solutions. And so don't panic because of the volume of stuff you're getting. It can be handled slowly on a problem by problem basis, and you can keep tons of notes. I have assigned some more problems which you will find in the eraser page under homework. It has been pointed out to me that you really couldn't find the homework pages before. I had a parameter set wrong in our eraser page, but that's been fixed, and you'll be able to see the homework problems now. So I'm not even going to write down what I assigned right here, but you can look them up in eraser. There is maybe just one more thing that I thought we would do, and that is, let me scroll. We said that this substitution would work if y prime was equal to some function that was first order in x and y, so ax plus by plus c. Now, I want to see if I can convince you of that. I'd like to find a really nice green. This might be the color that I'm looking for. So why don't we proceed the same way we've been proceeding? This will be more abstract though, but the next thing we would do would let v equal ax plus by plus c, and then let's try this. Then v prime would be a plus b y prime, and the constant would be 0. And so let's see, this is then v prime equals a plus b y prime, but y prime is f of, well, ax plus by plus c, but that's just a v. Ax plus by plus c, that's what we're letting be v. So this would be a function of v. Now what have I got? Well, now this is variable separable, and so I could write again if I chose, and I guess I do choose, 1 over a plus b f of v dv is equal to dx. And I've separated those variables, and so we integrate both sides, and, well, we don't really know in this case explicitly what the function is, and that wasn't the point of this exercise. This exercise was to show that if I have a function that looks like this, y prime is a function of this kind of a combination of x and y to the first power, then I can let v be the argument inside the uppercase f, and I will have a variable separable differential equation. And if I can evaluate this integral, then I've got a solution. This will be a solution v equal, but then I can substitute ax plus by plus c for v and solve for y, and I've got a solution. So general kind of procedure. We'll because I like to draw on my graphics tablet, we'll put a little solid block down there for QED. It's been demonstrated. So that's where we're going to quit on this short video, and this one will be pushed out to you on Monday. So have a good weekend and take care of yourselves and be safe and study differential equations. I'll be talking again with you very soon.